So in general, we want to develop some tools to help us determine whether or not a set of n solutions is linearly independent. And this will be through what's called the Wronskian function for a given collection of solutions. Well, before we can define that, I'll end up defining what's called the fundamental solution set, and this is directly tied to this concept of a fundamental solutions matrix to the homogeneous system. So a set of n linearly independent solutions to the homogeneous system star H phi1 to phi n is said to be a fundamental solution set to star H. And the matrix we'll call it capital Phi. That's built up by taking each one of these fundamental solutions, phi1 through phi(n), and making it a column of the matrix Phi. This will be phi1 of t is the first column of this matrix. And this is a matrix of functions. So phi1 of t, phi2 of t, all the way to phi(n) of t. Where the columns of this matrix are the fundamental solutions from the fundamental solution set. This matrix is called the fundamental solutions matrix, or the fundamental matrix. And it's important to note here that this is a very, very neat idea, because if you take this matrix and you take the derivative of this matrix, function of t, this is going to be the same thing as the derivative of all of the columns of this matrix. And because each one of these the columns is the solution vector to the homogeneous differential equation, this is the same thing as the matrix A times phi1, A times phi2, and so on and so forth, all the way to A times phi(n). Which is the same thing as A, matrix A, times the matrix phi1, phi2, phi(n), or just A times phi. where this is an n by n matrix. This is an n by n matrix. This is an n by n matrix. This is an n by n matrix multiplied by an n by n matrix, which results in another n by n matrix. And this fundamental solutions matrix satisfies a matrix form of the homogeneous differential equation itself, which is very cool. And we also know that this matrix has columns which are linearly independent to one another, because phi1 through phi(n) are all linearly independent to one another. So this means that our phi h, or our general solutions, or general solution, is of the form we said before: C1 phi1 plus C2 phi2 to Cn phi(n), which is the same thing as the matrix fundamental solutions matrix multiplied by some constant vector C. This is a very neat way of viewing the general solution to the homogeneous form of a differential equation. And we also have a definition now of the Wronskian. For n vector valued functions, phi1 to phi(n), the Wronskian determinant is defined as follows: W of phi1 to phi(n) is defined as the determinant of this matrix, capital Phi. And I'll be specific, capital Phi of T, which is the determinant of the matrix with columns of phi1 to phi(n). Where each of these, like I said before, I'll be specifically indicating here that these depend on T. They're all vector valued functions. And the reason that we're doing this is because this Wronskian contains direct information on whether or not n vector valued functions in Rn are linearly dependent or linearly independent on a given interval. And as such, it gives us a direct method for checking whether or not we have the correct fundamental solution set. So if phi1 to phi(n) are linearly dependent on the interval I, or for t and I, then the Wronskian is identically equal to 0 on I. And the proof of this, I'm going to sketch it out. So if phi1 through phi(n) are linearly dependent, then there exists some combination of phi1 through phi(n) that equals the 0 vector, but c1 through cn are not all 0. So it's relatively straightforward to go through and prove this in general, but I'm just going to show, we'll say, suppose that C1 is non-zero, C2 is non-zero, and C3, C4, and all of the higher coefficients are 0. Then phi2 is equal to negative C2 over C1 times phi1, and the Wronskian of phi1 to phi(n) is the determinant of the matrix capital Phi but phi2 is linearly dependent on phi1, so this is the determinant of phi1 negative C2 over C1 times phi1 to phi(n). And you'll remember from linear algebra that because this column of this matrix is linearly dependent on this column, the determinant is equal to 0. So this can be generalized to the general case, but I just wanted to illustrate, why this is working in this proof. And one of the big pictures here for us is that we can take the contrapositive of this statement, which is the statement, the theorem statement is, if phi1 through phi(n) are linearly dependent, then the Wronskian is 0. So that also means that if the Wronskian is non-zero, then these functions are linearly independent on the interval I. And this is the contrapositive of the previous theorem. So both of these are important for us. And we want to kind of get an idea of how the Wronskian is behaving for a general linear system that we talked about before. And we have a super nice theorem that's a very, very, very neat, has a very, very neat proof, and also has very, very neat implications for us regarding the Wronskian for solutions to homogeneous differential equations or homogeneous systems of differential equations. Now I want to note here that the inverse of this theorem is not true. And this is a very important thing to look at if you look at statements in mathematics, especially if you're taking a linear or a discrete mathematics course. That just because the Wronskian is zero doesn't necessarily mean that the functions are linearly dependent on one another. So for a great example of this, just consider the functions phi1 of t is equal to the vector value function t squared 2 times t, and phi2 of t is equal to t times the absolute value of t and absolute value of t plus t squared over the absolute value of t for t in the interval from -1 to 1. Going through and evaluating the Wronskian of these two vector value functions will give you that it's identically equal to 0, but the functions phi1 and phi2 are not linearly dependent on one another on this interval. So this is a very, very good example. And if we consider a plot of these functions, you should be able to see why. You do x squared 2x, x times absolute value of x, and x squared over absolute value of x plus absolute value of x. With each one of these colors right here, we can see that the bad part here is when t is negative. So from -1 to 0, these functions are clearly not linearly dependent on one another. This function, and then this function. If we restrict to positive t, this becomes, they become linearly dependent on one another. But including negative values of t gives us a very good counterexample to the inverse of this statement in general. And this leads us to a remarkable theorem called Abels' theorem, and it's due to the Norwegian mathematician Niels Abel. And this is the following. It's if phi1 to phi n are solutions to the homogeneous form of our system of first order differential equations on I, then either the Wronskian is identically zero, for all t in I, or the Wronskian is non-zero. For all t in I. And the proof of this is remarkable. And it starts by showing that the Wronskian satisfies the following first order ordinary differential equation. That the derivative of the Wronskian is actually going to be a trace of the matrix A of t multiplied by the value of the Wronskian at any given value of the independent variable, where you'll remember from linear algebra that the trace of a matrix is equal to the sum of the diagonal components of the matrix. This is A11 of t plus A22 of t plus A(n) of t. And this just relies on the fact that the Wronskian is a determinant of the matrix A of t, and using what happens to this determinant when you go through and take the derivative of it using the various derivative rules. You can directly show that it satisfies this differential equation. This is done out in the book for the case of 2x2 matrices, but it can be shown in general. And what's so nice about this is that this is a single first order ordinary differential equation that can be solved using the variation of constants formula that we talked about before. For a single first order ODEs. And when you do this, you get that the Wronskian as a function of time, or as a function of the independent variable, is the Wronskian at the initial condition multiplied by e to the integral from t naught to t of the trace of matrix A of tau d tau. In this function is either always 0 this is if the Wronskian at t naught is 0, or always non-zero. This is if the Wronskian at t naught is non-zero, because this exponential function is always non-zero. So this is very, very, very cool. And what we have now, finally, is we've come to the point where we can actually write down the general solution to star, the inhomogeneous problem